At a distance of 4 light-years, Proxima Centauri b is the absolute closest exoplanet to our solar system. It sits right next door, and its orbit is positioned perfectly within its star's habitable zone. But the habitable zone is often a mathematical abstraction. If your kitchen is 1,000 degrees and your bedroom is at absolute 0, your house technically averages out to a perfect temperature for liquid water. In reality, you are dead. Proxima b orbits a red dwarf. Because these stars are smaller and cooler than our sun, the planet must hug the star tightly, completing an entire year in just 11 Earth days. At this proximity, the planet is subjected to immense gravitational forces. The star's gravity is significantly stronger on the near side of the planet than on the far side. This differential physically stretches the solid rock of the planet, pulling it into a slight egg shape known as a tidal bulge. As the planet tries to spin on its axis, that massive bulge of rock is constantly dragged through the crust to stay aligned with the star's pull. Over billions of years, this internal friction acts as a planetary brake, eventually stopping the planet's spin relative to its sun. One side permanently faces the light, the other faces eternal night. On the dark side, the temperature drops so low that the atmosphere itself freezes. The air turns into snow and falls to the surface as solid ice, creating a massive low-pressure zone that vacuums the rest of the atmosphere over from the day side to be frozen in turn. Applying standard habitability math to these systems often describes a world that is actually a terrifying, airless, frozen graveyard. Survival on a world like this relies on a razor-thin margin, the Terminator Line. This twilight border sits exactly between the boiling hemisphere and the frozen darkness. This line marks a planetary heat engine. On the day side, the star superheats the atmosphere, causing air to expand and rise. It rushes toward the night side void, cools, sinks, and aggressively scrapes back along the surface to close the loop. This exchange creates a permanent hurricane-force wind tunnel. These winds churn the oceans and batter the twilight coastline under a sun that never sets. If these winds ever stop, the heat stops moving. The atmosphere would rapidly collapse into ice on the dark side, killing the world. On a tidally locked planet, relentless environmental destruction is the absolute prerequisite for planetary survival. We cannot launch a physical rover to a coastline 4 light-years away to scoop up dirt and look for life. The distance is currently insurmountable. We instead use the James Webb Space Telescope to peer into those alien storms from the safety of Earth's orbit. From our perspective, Proxima b occasionally passes directly in front of its star. During this transit, starlight passes through gas molecules blowing across the twilight zone. Specific molecules absorb specific wavelengths, leaving behind a barcode of black vertical lines. By reading which pieces of light are missing, we can perfectly reverse engineer the chemical weather of a world 4 light-years away. The search centers on identifying a highly specific chemical anomaly called a biosignature. Gases like methane and oxygen naturally react with and destroy each other. If left alone, they cannot coexist in an atmosphere for very long. If we see the barcode for both gases simultaneously, it proves that a massive biological engine on the surface is constantly replenishing them to replace what is being destroyed. Finding life thriving in such a brutal environment would prove that biology is a resilient, common consequence of the universe. Looking at the hellish extremes of our neighbor highlights just how rare our own world is. The fact that our planet turns, giving us a gentle sunrise and a quiet night,